What are they made of? Welcome back to School of Soul. I'm Adeline Atlas, 11 times published author, and this is the Humanoid Era series, where you learn everything there is to know about the new species arriving. If humanoids are meant to look, sound, and move like us, the question becomes, what are they actually made of? Beneath the soft expressions, fluid joints, and calming voices, what physical substances make up the synthetic body? Unlike machines of the past, cold, metallic, and rigid, humanoids are engineered for realism. They're built not just to operate in our spaces, but to feel human, chemically, tactically, and thermally. In this video, we examine the material science behind humanoid anatomy, what makes up their skin, bones, muscles, sensors, and internal systems. Let's begin with the outermost layer, the skin. Most humanoid robots use platinum-cured silicone rubber or thermoplastic elastomers, TPEs, to replicate human skin. Silicone is flexible, stretchable, non-toxic, and heat-resistant, which makes it ideal for areas that need to bend and flex like cheeks, forearms, and joints. It can also be tinted with precise pigmentation, giving it lifelike coloration, translucency, and even subtle veining. Some companies have embedded microparticles into the silicone to scatter light like natural skin, reducing that artificial plastic shine. TPEs, on the other hand, offer a softer, gel-like feel and are more commonly used in consumer-facing robots designed for touch interaction, like companionship bots or therapy assistants. They're also cheaper to produce in bulk. However, TPEs degrade faster over time and aren't as resistant to UV or temperature change, making them less ideal for long-term humanoid models. Higher-end humanoids stick to silicone for durability and realism. Now, underneath the skin lies a matrix of sensor systems and subdermal materials. This includes layers of haptic-responsive gel, a polymer substance that compresses like human fat and transmits pressure to embedded capacitive or piezoelectric sensors. These sensors give humanoids a crude sense of touch. They can detect when they're being tapped, held, squeezed, or brushed. Some are programmed to respond with subtle micro-movements, a blink, a head tilt, a tightening of the fingers. In more advanced systems, graphene-coated sensor films are used under the skin. Graphene is one of the strongest and thinnest materials known to science. It conducts electricity and can be stretched while maintaining sensitivity. When used in a mesh beneath synthetic skin, it allows humanoids to detect multi-point contact, meaning they can feel where and how strongly they're being touched, and respond proportionally. Moving inward, let's talk about the skeleton. Most humanoids have a skeletal frame made from titanium alloy, aluminum, or carbon fiber composites, depending on weight, strength requirements, and cost. Titanium is used in high-performance humanoids because of its high strength-to-weight ratio and corrosion resistance. Aluminum is used in budget models for lighter applications. Carbon fiber provides exceptional durability while keeping the weight manageable, ideal for humanoids expected to walk, lift, and move fluidly for hours. The skeletal design mimics human joint structures, with mechanical equivalents of shoulders, elbows, knees, and ankles. Joints are equipped with brushless servo motors, hydraulic actuators, or tendon-like cable systems that replicate the muscle tension release cycles of biological movement. Some models use electroactive polymers that contract when electrically stimulated, mimicking muscle fiber motion. These artificial muscles are still in early stages, but they're getting stronger, faster, and more responsive each year. The power source that fuels all this movement is typically lithium-ion battery packs, stored in the torso or pelvic region for balance. Lithium-ion cells are dense, lightweight, and rechargeable. Some humanoids use swappable modular battery units, allowing them to recharge without pausing for long downtimes. Others use ultracapacitors for burst energy, needed for sudden lifts, quick turns, or catching a fall. Emerging technologies are exploring solid-state batteries, which are safer, more energy-efficient, and capable of longer runtimes with smaller form factors. These battery innovations will allow humanoids to become slimmer, quieter, and more agile, less like machines, more like people. Now let's move to the brain, or rather, the processing core. Humanoids are not powered by a single brain like a human. Instead, they use distributed processing units, usually located in the head, chest, or hips. These units are custom designed for robotics and are often made with silicon-based chips, the same material used in phones, laptops, and industrial computers. However, humanoid processors are optimized for real-time decision-making across visual, auditory, and motor systems simultaneously. For example, a humanoid greeting a person at the door needs to interpret the face, recognize the voice, track limb movement, generate speech, and adjust posture, all in milliseconds. These calculations require edge AI chips built specifically to reduce latency and run advanced models locally, without needing to phone home to a cloud server. Leading chip manufacturers like NVIDIA, Intel, Qualcomm, and Tesla are developing humanoid-specific chipsets with dedicated neural processing units, NPUs. These allow for constant data processing from visual cameras, LiDAR, voice commands, and haptic feedback, basically turning the humanoid into a walking, talking, responsive supercomputer with an incredibly coordinated sensory network. Speaking of vision, Humanoids see through an array of cameras, usually embedded in the head or chest. These include RGB cameras for color vision, depth sensors for three-dimensional space, infrared cameras for low-light conditions, LiDAR units for spatial mapping and obstacle avoidance. Combined, this gives the humanoid full environmental awareness. Some models also use thermal imaging, allowing them to detect body heat, temperature shifts, or electrical hotspots. In service roles, this can be used for spotting fevers, identifying overheating equipment, or safely handling hazardous materials. Humanoids also include heating systems under the skin. Why? Because cold, plastic-feeling robots break immersion. Human skin naturally stays around 91 degrees Celsius, 33 degrees Celsius. To replicate this, engineers embed infrared heating coils or liquid loop heating channels just beneath the surface of the silicone skin. These heating systems are low energy and thermostatically controlled. They create warmth to the touch, especially in areas like the hands, chest, or face, where human contact is most frequent. Some advanced humanoids include pulse-mimicking actuators in the neck or wrist. These are not medically functional, but they simulate the slight rhythmic beat of a human pulse. It's another way to ease the uncanny valley and make prolonged interaction with a humanoid feel less artificial. Internally, humanoids are compartmentalized with sensor arrays, cooling systems, and modular plugins. There is no heart, no lungs, but there are internal equivalents. For example, a circulatory system might mean fluid tubing used for temperature regulation. A digestive system might refer to onboard power cells and chemical sensors. A respiratory system could be a fan array for active cooling. These are metaphorical, but they help engineers and developers structure components in anatomically familiar locations, balancing the robot's weight distribution to match that of a human body. Most humanoids are air-cooled, but some high-efficiency processors require liquid cooling systems, especially in the spine and neck. These tiny radiators pump coolant through closed channels, transferring heat away from chips during high-functioning tasks like running simulations, multi-person interactions, or extended navigation routines. Let's not forget audio systems. Synthetic humans are equipped with spatial microphone arrays, usually hidden behind the ears or in the chest. These allow the robot to isolate voices in noisy rooms, triangulate sound direction, and track overlapping speech. Audio input is sent to natural language processing engines, which convert human speech into machine-readable instructions. The response is then generated through text-to-speech engines, voiced through microspeakers, and enhanced with throat vibration mechanisms to avoid sounding synthetic. Facial expressiveness is driven by servo micromotors or shape memory alloys embedded under the skin. These create movement in the eyebrows, eyelids, lips, and cheeks. Advanced humanoids like Amica use up to 50 facial actuators just for expression, far from the complexity of a real face, but more than enough to trigger human emotional recognition. Then there's the issue of connectivity. Most humanoids operate on local command, but many include Bluetooth, Wi-Fi, and 5G modems, allowing for remote updates, cloud knowledge integration, and user feedback loops. This connectivity means the humanoid isn't static. It can learn over time, receive patches, or access online systems for translation, scheduling, or surveillance tasks. Finally, we come to ethics in materials. The rise of humanoids means a rising demand for rare earth metals, like cobalt, lithium, and neodymium. These materials are essential for batteries, magnets, and advanced circuitry, but their mining has ecological and human rights concerns. As we move into mass production, questions are emerging around the sustainability of these bodies. What is the long-term cost of building machines that replicate humans? Who mines their skeletons? Who recycles their cores? In short, humanoids are not built like computers or toys. They are chemically engineered, tactilely tuned, and structurally balanced to mimic human reality. Their skin is warm. Their joints rotate with natural cadence. Their cameras blink in sync with your face. They hear your tone, echo your phrasing, and look you in the eye. But beneath the realism is infrastructure: polymers, metals, semiconductors, batteries, fluids, and code. The illusion of life is constructed from some of the most advanced material science humanity has ever developed. Not for war, not for art, but for the replacement of human presence in everyday life. And that replacement will feel familiar, because it's been engineered to be. Hi, I am Adeline Atlas, 11 times published author, and SOS, School of Soul has a brand new series, the AI and Future Technology series. Look, you know the world is changing, and no, it's not going back to normal. Normal is over, and what's coming next is beyond anything we were prepared for. The School of Soul, AI and Future Technology series includes 319 videos on 1. The Download Society, How Data Has Replaced Destiny. 2. Predictive Future, Your next moves aren't random, they're forecasted. 3. Social Credit Systems, The Behavioral Economy Now Governs Access. 4. Hive Mind, Synthetic Telepathy and Collective Algorithmic Control. 5. Nanobots Inside You, Medical, Military, and Programmable Intrusions. 6. Grief Tech, AI-fueled digital resurrection and simulated comfort. 7. Uploading Your Mind, Consciousness Transfer and Data-Based Identity. 8. Deep Fakes plus AI Clones, The Replication of Reality and Identity Theft. 9. Quantum Humans, the merger of biology with quantum systems. 10. Digital afterlife, where your data goes when you die. 11. Resurrection science, reviving life through synthetic methods. 12. Immortal science, the end of death as we know it. 13. Longevity science, gene editing, anti-aging, and bio-upgrades. 14. Designer babies, engineered perfection before birth. 15. Artificial wombs, birth decoupled from the female body. 16. 3D printing, printing organs, limbs, and even humans. 17. The humanoid era, the rise of synthetic beings among us. 18. Legacy humans, the slow phase-out of unmodified analog people. 19. Smart cities, algorithmic environments that watch and decide. 20. Cloud-based societies, citizenship without borders or bodies. 21. Hackable humans, emotion, memory, and behavior under code. 22. Biometric scanning, your body is your password and your prison. 23. Sex tech, intimacy reprogrammed by machines. 24. Extinction of gender, fluidity, deletion, and design of identity. Every topic is fully explored with real-world technologies, patents, case studies, ethical analysis, and future forecasts. These aren't someday discussions. This is already happening. Join the SOS School of Sos Vault to overstand the future before it's implemented on you.